Hello, Chem 1110 students. We are beginning Chapter 3. And in Chapter 3, we're going to take a much closer look at how the electrons are arranged in the atom. And the reason this is so important, we know from Chapter 2 that the atom is made up of a nucleus, which has protons and neutrons in it, and the electrons around the outside. Well, as you might guess, when two atoms interact, it's those electrons that are actually forming the chemical bonds, allowing a molecule to be made. And those electrons are also what dictate what chemical reactions can take place. So understanding the electronic structure of an atom is extremely important. And to do that, we have to first talk about the energy of an atom. And this is just a general discussion of energy. You might hear this in physics. So energy is defined as the capacity to do work or to transfer energy. And so an example of that is that gas burner on your stove. It obviously transfers heat, transferring heat energy to the water you have in a pan or a tea kettle to boil. And so that work that it does is to pull those water atoms apart, or water molecules apart, so that they can go into the gas phase. You have a phase change there. And then if you have a whistling tea kettle, as those move and escape from the tea kettle, they actually go through a little orifice and cause the whistle of the tea kettle. Okay, so we know about the energy that is the capacity to do work, but there are other forms of energy, and we need to take a look at those. So we've got kinetic energy, which is that energy of movement. And as we discussed, it's often thermal energy because you have to heat it up to get things to move. And that thermal energy or kinetic energy is extremely important to chemists because it is a major portion of how chemical reactions occur, because atoms have to move to react. They have to collide, and they have to collide with enough energy in order to form chemical bonds. Okay, the other kind of energy is potential energy. And this is the energy that an object possesses because of where it is. If you stand at the top of the steps and you fall down those steps, you're going to move pretty fast. Or a skateboarder who's ready to drop into a half pipe. They're high above the half pipe, and so they have a lot of potential energy, which as they drop into the half pipe turns into kinetic energy as they move pretty quickly down the half pipe. And so there's two forms of potential energy that are of great interest to chemists. Once again, chemical energy, that energy that's stored in the bonds, and this has a lot to do with the electrons. And then electrostatic energy, and that's that attractive force of positive and negative charges, which are also extremely important when we're looking at how atoms interact, because those electrons cause the charges. All right, so the other thing you need to know about energy, and this once again you may have learned in physics, is called the first law of thermodynamics, or basically the conservation of energy. Energy can be turned from one form into another, that potential energy to kinetic energy. However, it cannot be created or destroyed. The universe has a set amount of energy in it, and you can't change how much energy there is. And so we're going to use that as we look at these atoms. And one of the major ways, one of the venues for looking at and investigating atoms was light and the color that can be obtained from atoms. And so we're talking about radiant energy. And we all know there is energy in light. We've all gotten sunburns, which shows you that the light from the sun has a lot of energy in it, and it can actually burn your skin. Well, that infrared energy from the sun is just part of an electromagnetic spectrum, and we're actually familiar with a lot of it. We've all had x-rays. We listen to television and radio broadcasts. We have a cellular phone. We use microwaves to cook our food. But the part we're interested in is light, visible light, because we are going to investigate the light, the colors we get from certain atoms. So you can see it's a very small portion of this full electromagnetic spectrum that's, makes up the universe. So there was a lot of study of light, and the speed of light is extremely fast, much faster than the speed of sound. It's 3 times 10 to the 8th meters per second. It's constant in a vacuum. So that's how fast the sun travels, or the light travels from the sun to the earth, because it's moving through the vacuum of space. And we see that not only is it equal to a value, but that speed of light, which is given the letter c, is equal to its wavelength times its frequency. Wavelength, I think you understand the length of a wave, but the frequency is, if you stood at one point, you could see the crests of the wave go by. It would be how many go by in a second. And so wavelength or frequency is known as reciprocal seconds, and that unit is often called hertz. All right, so back to the study of the atom. The first person who put forth a plausible and useful theory of the hydrogen atom was Bohr. And, he said, well, the light from the sun is composed of a lot of colors. Physicists knew this because if you put it through a prism, you see all the colors, Roy G. Biv. And they all run one right into the other. The other thing scientists knew is you could get an emission spectrum by heating something up. So an example from our everyday life is that filament in an old-fashioned incandescent light bulb, which you really can't buy anymore. But when you stimulate those with electricity, you get very bright light that you can see by and you can read and that kind of thing. But the emission from a heated solid or from sunlight is continuous. All the colors of the visible spectrum are there. However, if you heat up the gas that is of an element, you don't get all the colors. You get what we call a line spectrum. And so the way this experiment was done is very simple. You had something like a cathode ray tube where you had, a high voltage electrical energy put through a element gas. You narrow it down with a slit, you put it through a prism, and you separate the wavelengths, but you don't see all the wavelengths. You only see certain ones. And the simplest one was from hydrogen. And just to show you some of the other ones, scientists love to do this. They were investigating everything, and you can see all these elements that they did that had various line spectra. And there, just below the halfway point, is hydrogen. And hydrogen has 4 lines, as opposed to the multiple lines from these other elements. And so Bohr was very interested in it and thought, well, that's a good, unique one to use. It only has 4 lines. Let's investigate why it's not a continuous spectrum. So he said that the reason we only get certain lines is because the energy that we saw as light was due to the electron in hydrogen going from its ground state, where it hangs out most of the time, being promoted to a much higher level, and then by energy going into it, so maybe the electrical energy that's put into that cathode tube, and then it can't stay up there. It's like throwing a ball up in the air. It doesn't stay at the apex. It falls back down. And when that hydrogen electron falls back down, it generates light energy, and it's of a particular wavelength. And so he said there's only allowable places for this electron to go. And that's why you always get the same color over and over. And he was able to calculate, based on the energy associated with a color, what those levels were. And he called those levels N. So when N equals 1, he said that's ground state. So it's just the first level. It's the lowest energy of the atom. It makes it very stable. Nature always prefers the most stable state. And if the electron's promoted to another level that it can go to, that's called an excited state. Okay, so I have a little graphic on this one that shows a funny stair step, and each of those flat portions of the step are a place where the electron of hydrogen can sit, but it can't stay up there very well. So what happens? Radiant energy is absorbed by that atom, or electrical energy, and it causes it to move from the ground state to an excited state. So it goes to an upper step. But it can't stay there, so it falls back down. And when it falls back down, it's going to go to a lower energy state, or the ground state, and it's going to emit that as light. And this is called quantized movement because it's not a ramp. It's a bunch of steps. It's just specific places where this electron can sit. And the diagram shows it as a ball. Obviously, that's not an electron, but we're just trying to grasp the concept here. Well, this is a very simple diagram of an atom, the hydrogen atom, that Niels Bohr, came up with. And he said you have the really black dot in the middle, which is the nucleus, has a proton in it, and then you have 3 different energy levels labeled N. And so it's 1, 2, and 3. And what my little red dots are showing there is the electron falling from the N equals 3 to the N equals 2, and you get a wavelength of light out, and that energy is Planck's constant times the frequency. So you can figure out the color you would get from that. All right, so he actually developed an equation, and as I say, that change in energy is equal to h nu. H is Planck's constant, and nu is the frequency, and from that you can calculate those energy levels. Not that I'm going to ask you to do that calculation, but it can be done. And so from that, you can get the wavelength, and that's what the lambda Greek letter is there. And so you can come up with what the color is. And he knew the colors that were emitted, and he was able to diagram, those electrical levels, or the energy levels, the allowed quantized levels the hydrogen electron could go to. Well, it was a great advance. The Bohr atom was, really gave people a leg up on understanding the structure of the atom. And in fact, Niels Bohr won the Nobel Prize in 1922. However, it only worked for hydrogen, and unfortunately, there's a lot of other elements. So new models were pursued by other researchers. And we will go on in our other videos about that.